Hello, and a warm welcome to this talk. My name is Lennart Wissel from the AI in Hannover. On behalf of the LISA Pathfinder collaboration, I have the pleasure to highlight some of the key results of the optical metrology system aboard LISA Pathfinder. I hope you enjoy the talk. LISA Pathfinder was basically one LISA arm squeezed into a single, well-controlled spacecraft, operating between 2015 and 17. However, it generated a lot of data, and all of that data is still analyzed today and still informs us today about some of the performance characteristics that are helpful for LISA. The launch was in December 2015 from Kourou in French Guiana. It followed a transfer period to its final destination from Earth to Lagrange point 1, almost 1.5 million kilometers away. And I still find this amazing that the data that I'm going to show in this talk was generated so far away at a single spacecraft, and everything was well behaved. The core instrument of LISA Pathfinder, depicted here on the left, consisted of two test masses, a gravitational reference sensor surrounding those, and an interferometric readout on the optical bench in the middle between those. On the right, you see a schematic of its functionality. Test mass 1 was in free fall along the x coordinate, joining the two test masses. The spacecraft was in a drag-free configuration to follow this test mass. Test mass 2 was also freely floating, following the test mass 1 and the spacecraft. The main results that I think all of you know are that the demonstration was possible that the two test masses in LISA Pathfinder could be put into free fall at very low frequencies, so at millihertz and below, with differential acceleration that was even better than what is required for LISA. And you can see that in the plot on the bottom left here. The red curve was one of the best runs that we had. What you don't see here so much are the high frequencies. And the high frequencies are actually where you can see the influence of the interferometric system. And that's why I'm switching to this plot here now. This is from the earlier publication of the main results of LISA Pathfinder. And here you see this f² raising noise shape at high frequencies, which is due to the optical metrology system readout. And in this case here, we look at an acceleration spectral density. The main readout is in displacement, so in meters, and then the calculated noise spectral densities are in meter per square root hertz. And this is what I will focus on in this talk. Here on the right-hand side, you see in blue, essentially the delta G curve in raw displacement. And it's compared here against the requirement of the optical metrology system and the ground measurement in orange. And you can see that compared to both of the ground measurement and the requirement, we are a big amount better, performing much better than required, especially at high frequencies. And how this noise curve exactly behaves and how it can be characterized and budgeted will be part of this talk. And why is this important? Because the LISA local interferometry, the test mass and reference interferometer will be very similar to what was flying in LISA Pathfinder. This is the area of interest in this talk. How did the OMS actually work in principle? So there was a laser unit that produced the laser light at 1064 nanometers at about 35 milliwatts. This was then fiber delivered to a modulation stage where the beams were split up, where the beam was split up into two beams, and then frequency shifted using two AOMs. The frequency shift was such that the difference frequency, which is then the heterodyne frequency, was at 1 kilohertz. These two beams were delivered to the optical bench via fibers, where the interferometers were measuring the test mass, displacements, and so on. This was then used to control both the thrusters and also to control the laser system itself, to control, for example, the frequency noise or the power stability of the optical system. A phase meter measured the phase from the, so basically converted the resulting photo current from the optical bench, from the photodiodes, into a phase, which was then then used to perform all these tasks. The interferometers are again depicted here. You can see the electrode housing with the two test masses at the sides, and in the middle you can see an illustration of the optical bench with in green the two fiber outcouplers. Then the laser beams are highlighted in blue and red, and you can see this silver, in silver, the photodiodes. These were in general quadrant photoreceivers. 4 interferometers on the optical bench. Here are the 4. First, the X12 interferometer that measured test mass 1 to test mass 2 displacement. This was the main sensor here, and most of the plots that I'm going to show are based on this measurement. Then there is an X1 interferometer that measured the displacement of test mass 1 with respect to the optical bench, respectively the spacecraft. There was a reference interferometer that measured common path length noise in the fibers, and this measurement was subtracted from all the other measurements to reduce common mode noise. And then there was a frequency interferometer used for the frequency control and also to estimate later the coupling strengths into the main measurement, the X12 measurement. As an overview and labeled everything together, this was again the optical bench with the coordinates of the two test masses, and the OMS did not only provide the longitudinal measurements but also the angles of the two test masses in 2 degrees of freedom each. This was done using differential wavefront sensing. And here you see a picture how this looked in reality just before boarding the flight. So what happened then in flight? Basically an immediate success. The test masses were released in mid-February 2016, and then the test masses were aligned one after another. And after initial release, the contrast was still low, but after alignment of both test masses, you can see that in both the main interferometers, the contrast was reaching around 99%, which is a huge quality statement for the alignment of the interferometer. And on ground, only 93% was possible, which is still a pretty good value. Coming back to the main performance of the differential test mass to test mass measurement, we had this huge improvement compared to the ground, but also this much better performance compared to the requirements. The question now is, can we actually understand the blue curve here in flight? And well, can we explain the sensitivity? Here I switch the plot and you can already guess, yes, we can. And this was already published. The noise model was already published in an earlier publication last year. And the question is, how does the sensitivity, how is it influenced? And one of the main noise sources are the phase meter readout noises. So basically the ADC noise and the electronic noise in the readout system. And this was measured on ground, and it already reaches the noise floor at the high frequencies. Since the reference interferometer is also subtracted, it also adds to the noise here. Next, we have the frequency noise coupling. This was characterized by specific experiments with the mismatch of the different interferometers, such that we could estimate its influence here. And you can see, especially at this frequencies, that it has an influence, and towards lower frequencies, which is the main focus, it drops rapidly. Then there are RIN and shot noise, which are here drawn together because they happen to be at the same strength in this case. And the shot noise is calculated from the average power in the interferometers, and the RIN coupling is estimated from indirect measurements and experiments that were performed close to this measurement. There's also another noise source, which is small vector noise, which is quite low due to a specific control loop, but I won't detail that here in this talk. We have an estimate for the thermally driven noise on the optical bench, for example, due to the N over dt dependencies, but you can see that it is below the measured noise. And this high frequency noise is actually estimated from or follows a Brownian force noise dependency that is well estimated from the main delta G, so the main differential acceleration experiments. And overall, in total, we see that we have a total OMS noise budget, which defines this dark red curve here. You can see that we hit the noise shape quite well at higher frequencies. So a few questions remain actually here. One is, for example, this mid-range bump. And this is basically due to spacecraft jitter. And it's called tilt-to-length coupling. And there will be a dedicated talk on these are Pathfinder TTL by Marie-Sophie Hartig. Furthermore, we have this pretty impressive around 30 femtometer per square root hertz sensitivity at higher frequencies. The question is, of course, is that valid at for different operational conditions? And how's the long-term performance of this? And secondly, is this noise model also valid towards lower frequencies? Here, of course, we have the problem of the Brownian force noise moving actually really the test masses, such that we cannot really validate that noise model here. And I will now go focus on the red and the green box, and starting with the low frequencies. And the question is, of course, how can you disable the low frequency effects? And for Pathfinder, it was, of course, required to grab and fix the test masses during launch, and they had to be released later. So during one of these grabbing of the test masses, the test mass motion is, of course, reduced towards even lower frequencies. And this is where we took this measurement. You can see here in black, again, the differential test mass to test mass measurement. And what you see is the noise model and the noise shape is now flat even towards millihertz. And in red, again, we applied our noise model in the same way as I explained before. We are still below the requirement, which is still in the range of the LISA local requirement as well. And what we can see is that our noise model now explains the noise behavior in that flat sense also towards low frequencies, which is basically due to the very low contrast, due to the misalignment that happens when you actually grab the test masses, creating this, in a sense, bad sensitivity. And what we can also see is that our estimate on the thermally driven optical bench noise was a bit too pessimistic even. This was in a sense expected because we did not include any common mode path length effects on the two beams for this noise source here. So in general, we can say from these investigations that our noise model seems to be valid also at lower frequencies, and that we have no reason to assume noise sources that would come in at these frequencies at better sensitivity, so at higher contrasts. So next will be then the intermediate contrast. What happens? How does the sensitivity change at intermediate contrast? Can we still explain the noise at that point? And for this, we did an experiment. We tilted both test masses pseudo-randomly. The tilt of the test mass changes the beam overlap on the quadrant detectors such that the contrast is lowered. Then what we did, we took this high frequency range and averaged the noise spectral density there, which was usually this 30 to 40 femtometer per square root hertz. And those we plot then over the contrast estimate. And we did this here for the X12 interferometer. And we measured the noise again in the differential displacement of the two test masses. Then we fit the two free parameters that we basically don't know and we cannot measure independently in flight, which is the relative intensity noise of the laser and the ADC noise level. And the result is here shown in the plot. Blue are the sensitivity, so the noise estimates of the differential measurement. And in red, the red points are the noise model estimates after this fit. And you see the contributions of phase meter noise, of RIN, and shot noise and frequency noise here. And you can see that we can explain almost everything in the noise shape here, which is quite astonishing over this big range of contrasts. As expected, the phase meter noise has this 1/c dependency, while the RIN is relatively stable and only couples via a geometric piston while tilting the test masses. So this gives us a good confidence in our noise model actually for the behavior of the sensitivity. What is now about the long-term sensitivity? So these were singular examples during the mission. What is over the whole mission? And over the whole mission, there was basically a lot going on. We had station keeping maneuvers, different experiments going on, spacecraft cooling, and so on. But there were also certain periods where we only measured noise. And this is shown now here again, basically over the time of the mission from launch to the end of the mission. We see in black, again, this averaged high frequency sensitivity of the differential test mass to test mass displacement. And we are here around our 30 femtometer per square root hertz. And we see that throughout the mission, we only see little changes in this overall level, which is well below the requirements. However, we see that there are two levels. We see a lower level and a few noise states also in an upper level that changes over time. We could relate this upper level to 2 states of frequency noise in the laser. And there were ongoing investigations to characterize that. And what we see in red is the noise model using the frequency noise data and a fit for the RIN to actually see if we can explain all the changes. And as you can see, our noise model fits the data pretty well in the longitudinal measurement. We also did this for the angular degrees of freedom in the X12 and X1 interferometers. And this is what we have here at the bottom. And here we see first 4 different colors. These are the 4 different angles measured. And you see a much broader distribution of noise states than in the longitudinal measurement on top. This has certain reasons. First, we see a very good sensitivity of even below 100 picoradian per square root hertz for DWS at the beginning of the mission. And then we see jumps in the noise levels. And this jump is due to alignment of the test masses. There are offset dependent noises, such as relative intensity noise coupling, that increases for given test mass rotation in the DWS readout here. And you can see again in the dark lines our noise model applied in the same way as for O12 here for DWS. And you can see that we explain most of the changes pretty well in DWS as well. However, there's at least one big jump that we cannot explain fully with our current model. We tried many different ideas, but given the restrictions that we have, that we cannot access and run the satellite again with different experiments, and that the data we got is also limited in both sampling frequency and also in density, we cannot really understand what happened here. However, all these unexplained change is still well below any requirement, and we see a very good sensitivity also in DWS. One last very important aspect of LISA Pathfinder is how stable and reliable was it. The LISA mission will be much longer than LISA Pathfinder. However, LISA Pathfinder also operated for 1.5 years. So we can already see, derive some important hints from LISA Pathfinder here. One of them is basically how well aligned does the optical metrology system stay over the course of the mission. And for that, spot position measurements were performed throughout the mission. That means that always one beam was turned off, and the power distribution on the quadrant photoreceivers was then measured to estimate where a certain beam hits the photoreceiver. And this was done for both beams many times over the mission. And you see that here on the right hand in the plot, with for each beam, for the measurement and reference beam, always in the X and Y direction. And especially during the main mission period, you see a very stable behavior, somewhat correlated with the temperature here in black, as expected, but still very stable, only micrometer changes. There was a certain cool down experiment on LISA Pathfinder. It was highlighted here in this light blue, where you see bigger changes in a certain degree of freedom. There are other investigations ongoing for that. However, this was an experimental situation, and the main data shows very good behavior and stability. Another very important aspect was the photodiode responsivity. Since LISA is in the long arm interferometer dominated by shot noise, it's very important that the photodiode responsivity is quite high so that we don't lose more photons there. And these INGAS QPDs were performing quite well. Here you see the 4 effective Photodiode responsivity for the 4 interferometers aboard the Pathfinder. And you can see that within the error bars, there were basically no change throughout the mission or the investigation duration here, which is quite impressive. Also, we couldn't observe no contamination on the optical components, and this was derived from the power transmission, and this seemed also to be quite stable. Another very important aspect is the laser and phase meter performance and the overall duty cycle of the optical metrology system. And this even reached 99.4% of the whole mission duration. And what is shown here is the reference contrast estimated from a certain set of housekeeping data. And we can see that the reference contrast was very high and very stable throughout the whole mission, with a few exceptions. And these are, for example, the spot position measurements, where of course don't have a contrast during this when one beam is turned off. So overall, very stable and reliable. And this already then brings us to the key message here, that this was really a big milestone, that we have good understanding of the noise budget, that it was very stable and reliable in the performance, that the displacement sensitivity of about 32 femtometer per square root hertz and DWS of even below 100 picoradian per square root hertz was very impressive, unprecedented, and so good that the local interferometry on LISA can already be done with the performance that was demonstrated in LISA Pathfinder. There are some related talks I would like to highlight here. And the first two are specific Pathfinder talks, and then there are more general and LISA-related talks that are all, in a sense, also building on LISA Pathfinder. Yeah, I would like to highlight all the OMS contributions here. LISA Pathfinder was a big team effort, and I'm very grateful that I was part of this team. And this was really one of the biggest highlights for me, the team itself that enabled all the science. And yeah, with this, I turn myself on, and I hope you enjoyed this talk as much as I did, and wish you a good day. Thank you.